I'm pleased to introduce Murty from Queen's University. We'll speak about the relation between Nagao's conjecture and BSD conjecture and related topics.
Okay, good. Okay, well, firstly, let me thank the organizers to invite me to this global experiment on how seminars are going to be conducted or conferences are going to be conducted in the country. So this is joint work with Seoyoung Kim, who is a Coleman postdoctoral fellow here, kind of an outline for the talk. So the talk will have 6 parts. First, background. Second, history and motivation. 3, our main theorem. 4, the idea in the proof. 5, relation to Nagao's conjecture. And 6, if time permits, it may not, but anyway, let's just put this down, future directions. Okay, so that's the outline for the talk. Let me get myself in order here. So let's begin with a little bit of the background. Of course, based on the talks earlier, it's clear that most of you already know a considerable amount of material about elliptic curves, but let's get the notation in order. So you have an elliptic curve. We will take the elliptic curve over the rational numbers. And the discriminant of the elliptic curve is going to be denoted as delta sub E. And the conductor will be n sub E. And as all of you know, the classical theorem of Mordell-Weil tells you that this is a finitely generated abelian group with a certain rank R. I'm trying not to hide. I hope people can, I'm not blocking what I'm trying to write some stuff about. I hope people can see. This is a classical theorem of Mordell, and it was generalized by André Weil to arbitrary number fields and i's in general. And what we will do is for primes not dividing the discriminant, we will look at n sub p, which is the number of points on the elliptic curve, and including the point at infinity, you can write this as p plus 1 minus a sub p, where we have the famous Hasse inequality, a sub p is less than 2 root p. And for primes dividing delta E, you have AP either 0 or plus or minus 1, depending on its reduction. And with this definition in place, one defines the L function attached to the elliptic curve. So for primes dividing delta sub E, we have 1 minus a sub p over p to the s inverse. And from primes not dividing delta sub E, you have 1 minus AP over p to the s plus p over, oops, that. By the way, am I supposed to turn the microphone off on my side? Do I turn them? Oh, no, I don't. Otherwise, you won't hear me. Otherwise, you won't hear me, right? I mean, it's I can't mute my microphone. Yeah, you won't hear me. Okay. Anyway, that's the definition of the L function of the elliptic curve. Because of Haas's inequality, AP being bounded by 2 square root P, this converges absolutely for real part S bigger than 3/2. And as all of you know, the product, infinite product, can be expanded into a Dirichlet series. And the Dirichlet series, we can write LE of S. Let's see, is this visible? Let's see. Yeah, okay, good. LE of S is summation n going from 1 to infinity, A sub n over n to the S. And the modularity conjecture, now theorem, tells us this is these coefficients A sub n's are Fourier coefficients of a modular form of grade 2. And we have all the classical knowledge that you have with respect to these kind of zeta-like functions. We have extends to an entire function for all S in the complex plane. And we have also that the lambda S, which is the conductor of the curve to the power S over 2, 2 pi to the minus S, gamma of S, LE of S. This is entire and satisfies a suitable functional equation. The functional equation is lambda 2 minus S, where W could be plus or minus 1. So this is a beautiful theorem, the modularity conjecture, proved by Wiles and company. And we have this knowledge about the L function. And so we can talk about S equals 1 now. If originally the Dirichlet series only converged for real part S equals 3/2, but now, since it's an entire function, we can talk about S equals 1. And the Birch Swinnerton-Dyer conjecture, as it's normally stated, is that the order of the zero at S equals 1 of LE of S is the rank of the Mordell vehicle. This is the conjecture. Now, the interesting thing is, this is not the original Birch Swinnerton-Dyer conjecture. The original Birch Swinnerton-Dyer conjecture actually was inspired by some sort of local global principle, if I can call it that. And if you go back to the early 60s and check the papers by Birch and Swinnerton-Dyer, you'll find that the conjecture that they were actually making, so this I'll call the original Birch Swinnerton-Dyer conjecture, the OBSD conjecture. O standing for original. That the product of the primes p less than x of np over p should be asymptotic to some constant. Okay, subscript here, log x to the power r. So r is the rank. Where's that put the here? Rank r. So that r is there. And then the NP is the number of points on the curve. And so this was the original Birch Swinnerton-Dyer conjecture. Before they had this finer version of the order of the zero has to be the rank of the curve, they experimented numerically in a series of papers, beautiful papers, by the way, and managed to make this kind of a local global principle idea that somehow information about points modulo p should, for a sufficiently large number of primes, should give you information about the rank, some global idea. The local information number of points should give us the global information about the rank. So this is this was the original Birch and Swinnerton-Dyer conjecture. Okay, now several people have noted at that time, I suppose, but nothing was in print until 1982. But several people noticed that this was too severe a conjecture. And so let me kind of move now into the history and background, history and motivation, rather. Let's see, where are we? Okay, yeah. So first, Goldfeld, around 1982, noticed that this conjecture is too severe, and proved that OBSD implies LES as satisfies Riemann hypothesis. The analog of Riemann hypothesis. So what the analog of the Riemann hypothesis is, where are we here? So this, we have a functional equation S into 2 minus S, and so the line of symmetry is S equals, real part S equals 1, and therefore one expects all the non-trivial zeros to lie on the line real S equals 1, and so that's what we would get. Then he also made some interesting comments about C sub E has to be modified. Is this too small? Can people read that? You're okay with that? Okay, good, good. So C sub E has to be modified according as E has CM. E has CM or no CM or no CM. And so that was an important point as well. So this heuristic that mod P information should give us the rank, and along with this constant had to be modified a little bit. So that was the first paper. I remember musing over this result ages ago, and my interest in trying to come back to this original Birch and Swinnerton-Dyer conjecture was motivated by largely questions asked to me by John Coates in the 80s. And his question was basically, is there a way to get the rank from the A sub P's? And somehow just doing finite number of computations, can you actually get your hands on the rank? And the answer is, I would say conjecturally, yes. Hopefully that will come out of this talk. So in that context, I wrote a paper with Wentong Kuo, who was a postdoc of mine in the 1990s, late 1990s, I suppose, and myself. There's another parallel paper around the same time by Keith Conrad, and all of us observed that what is this? We were trying to figure out what is this conjecture and how does it relate to the Riemann hypothesis. I mean, it implies the Riemann hypothesis, but what is does it go the other way? That's one of the questions. Does it go the other way? And the answer to that is it doesn't go the other way. That's the important point. In some sense, this conjecture is stronger than the Riemann hypothesis. And so the question is, if it's stronger than the Riemann hypothesis and we don't even know the Riemann hypothesis, is there any basis for believing this? And that's what piqued my interest in that time. So let's go back to to kind of state these results. Let me just say that the L function, we will rewrite this L function. Better watch my time. We'll rewrite the L function as, primes dividing delta E 1 minus AP over P to the S inverse primes not dividing delta. Oops, I shouldn't cram this. Let me write it neatly here. P not dividing delta E, and we will rewrite this Euler factor as 1 minus alpha P over P to the S inverse, 1 minus beta P, P to the S inverse. I mean, this is in line with this conference talking about Sato-Tate, which is about, these alpha P, beta P anyway. So alpha P and beta P have absolute value root P. So this is I'll rewrite it like this. And once having rewritten this in this fashion, then we can find out that we can prove that the original Birch Swinnerton-Dyer conjecture is equivalent to the assertion that P to the K less than or equal to X, alpha P to the K plus beta P to the K times log P equals little o X log X. Keep in mind, the line of symmetry is S equals 1. So the power X to the power 1 here makes sense. That's the line of symmetry. In the classical prime number theorem, the error term in the prime number theorem is expected to be X to the half, because the line of symmetry is 1/2. Here the line of symmetry is 1, therefore you get something like X. But then in the classical case, so you have this, and just to make comparison, let me just put here comparison that the Riemann hypothesis for LE of S is equivalent to the statement that the same sum, P to the K less than X, alpha P to the K plus beta P to the K log P is big O of X log X squared. So I hope it's if I'm writing too small, let me know, okay? Just tell me. But I hope this is visible. So here we have the classical, the Riemann hypothesis for the L function of the elliptic curve is equivalent to the statement that this sum is O of X log X squared. But the original Birch and Swinnerton-Dyer conjecture is equivalent to the statement that it's little O of X log X. So you can see a substantial strengthening is being predicted by this local global principle.
Hello, Ram. So there's a comment that the exponents are too small to read.
Ah, okay, good.
Like,
that's good.
Yeah.
Okay, so this should be, this is a 2. And there's no exponent in this one, it's X log X.
Okay, and then that's the summation P to the K less than X, right?
Yeah, that's the summation P to the K less than X, alpha P to the K plus beta P to the K, exactly, yes.
And also for the equivalent statement for RH.
Yeah, this one also, yes. And the point in these calculations is that usually it's only K equals 1 that matters. K equals 2 and higher are under control. So that's just like when you're trying to count the primes and prime squares and so on and so forth, it's essentially the primes that give the main term, and the squares and cubes and so forth are negligible. So that's
there's another question that whether the rank is not involved in the statement of either Riemann hypothesis or OBST.
Yeah. No, OBST has the statement of the rank here. So this is maybe not big enough. This is the rank right there. That's the exponent. See, the product of NP over P, P less than X, is asymptotic to a constant times log X to the power R. R is here. But in the Riemann hypothesis equivalence, there's no rank. Doesn't come in. Thank you for that. Now, so this opens the door for a discussion as to what is the error term in these things. I mean, so, and this question has actually been investigated by two people before, not in this context, of course, but it was in the context of the classical Riemann zeta function. That was Montgomery on the one hand and Gallagher on the other. So let me just try to explain what Montgomery and Gallagher did with respect to the classical. So let's just call this psi sub E of X here. Psi sub E of X is the sum. This whole sum here, we're just going to call psi sub E of X. Okay. Now psi of X is the classical Chebyshev function which is basically summation log P to the K less than or equal to X. So P is always a prime. So that's the classical Chebyshev function. And all of you know the prime number theorem says that this is equal to X plus some error term E of X. And if it's E of X by the prime number theorem is little o of X. And the Riemann hypothesis is equivalent to the statement that E of X is big O of X to the half log squared X. And Montgomery, using probabilistic methods, ideas kind of inspired by probability theory, which is it's a new it's a kind of a nice paradigm to use for understanding prime numbers, zeta function. Montgomery and Gallagher, what they did was they used probability theory to predict that conjecture that E of X should be O of X log X squared. Now, as you know, it's not a talk in analytic number theory unless you say log X. Okay, so this is the signature for a good analytic number theory talk. This is their conjecture. So you can see that here the error term is predicted to be X log X squared, but they're predicting that it should be much smaller, X log X squared. And so what the original Birch and Swinnerton-Dyer conjecture is predicting is little o of X log X. So if we have sorry, this should have been a half. Maybe that's part of the confusion. Okay. In the classical case of the Riemann zeta function, this is what they were conjecturing, right? This thing. And so if you now translate their analysis to the context of the L function of the elliptic curve, this suggests in our case, you see this X comes from the simple pole. In our case, there's no pole. So we just expect psi sub E of X to be O of X log X squared. That's what we would expect. And so if that's what the probability theory kind of suggests, it's quite possible that the original Birch and Swinnerton-Dyer conjecture is true. Because there's a lot of leeway between this one, this log, triple iterated logarithm, and little o of x log x is a it's not too bad. You're supposed to kind of decrease this thing by a little bit. So this is basically where things stood, and I think. Any question? Yes, I hear something. No? Okay. So this is where things stood for a while until Seoyoung and I started working on this while she was here. Well, she's still here, so we still haven't finished it. Actually, we're almost finished, and there are a few more things to do. But anyway, so we started thinking about it, and an old paper of Harold Kramer came to my attention. I started looking at it, and I noticed that there's a nice technique there where he's trying to analyze, so that this is on Kramer's name. Kramer wrote a paper in the 1920s where he was also trying to understand the, where is that paper? 1922, he wrote a paper thinking about what the error terms should be, or what, he didn't make these kind of conjectures though. But what he proved is very interesting. He proved the following. So it's not in this paper, but I can do it from memory. What he proved was basically, if you take psi of t minus t, square it, I think there's a t here. Let's see. Yeah. So this is the quantity that he looked at. 1 over log x, integral 2 to x, psi of t minus t over t squared, psi of t minus t squared over t squared dt. Okay. What do you think this should be like? So if you have the Riemann hypothesis, this is going to tell you it should be like root t times log t squared. Okay, so that's what it's telling you, that this should be like root t times log t squared. And so when I square it, it'll be t times log t to the power 4. And the t would cancel here, one of the t squares, and I would get a 1 over t, and I get a log t to the 4 on the top. And then essentially that turns out to be log x to the power 5. When you divide by log x, you would get something that goes to infinity. That's what if you just use the Riemann hypothesis, you wouldn't be able to say this is actually finite. So what he proved is that this tends to a finite limit. So this is modular Riemann hypothesis. So Riemann hypothesis implies. So assume the Riemann hypothesis. So I told you, if you assume the Riemann hypothesis in a naive way, just plug in the error term that you know, you're not going to get anything like this. But if you are careful, if you take the explicit formula, as it's called, and not just any old, it's the truncated explicit formula. So you have to do a little, I mean, this is not a trivial theorem to prove. You have to take a truncated explicit formula with some error terms, crank this through carefully, do a very careful analysis with a zero thing, and then lo and behold, there's some sort of Parseval theorem that kind of shows up. Some sort of Parseval type result shows up here. This, if you can't read it, let me just read it for you. It's 1 over mod rho squared, where rho's are the zeros of the zeta function, non-trivial zeros. And here on the numerator is the multiplicity of the zero. N rho is the multiplicity of rho squared. Okay, so this is what we have. And so this is actually a beautiful result. And what it tells us is that this error is like root t. That's what it, you see, if you have root t there, that will be, when I square it, I'll get a t, and t over t squared is 1 over t dt. And if I integrate that, I get a log x, and that cancels with the log x, and more or less get 1. But essentially, that's what this is saying. This is a remarkable theorem. And so the question now is, can we, what's called a transport the structure? Can you transport these ideas to the context of the L function of the elliptic curve? And indeed, there's not a difficult thing to do, but you have to do the same old careful analysis that Kramer does. Do it, crank it through, and it turns out that what does it turn out to be? It turns out, where did I put this thing? I did call this psi. I call this psi sub e of x, right? This is psi sub e of x. Okay. This is psi sub e of x. This is what we're after. So the theorem, so our main theorem, but this is not the main theorem, sorry. This is a step toward theorem 1, is that assume LES satisfies RH, then limit x goes to infinity, 1 over log x. Oops, not summation. Integral x psi e of t squared t cubed. There's a small, adjustment because this line of symmetry here is 1/2. The line of symmetry here is 1, so there's an adjustment. So don't worry about this silly t cubed here, but this turns out to be exactly rho n sub rho squared over mod rho squared. So this is, of course, these are zeros of the LE of S, and not here. These are zeros of the Riemann zeta function. Here, the zeros of LE of S. So LE rho equals 0. So anyway, you get the same result, which tells you now that psi e of t is probably root t on average. And so when you have root t there, it becomes, t, because the central line is 1. So t squared, and then you get a log x, and that you. So essentially, this suggests that psi e of t is usually, whatever this means, usually around t. Oops, around t. Whatever that means. So there's some hope in trying to kind of explore the original Birch-Swinnerton-Dyer conjecture using this result. So that's what we'll do right now. Okay. So having this result in hand, what do we do now? Okay, what do we do now? Well, we do the following. First thing, theorem 1 implies that the integral 2 to x psi e of t squared dt over t cubed is asymptotic to some constant. Let's not put asymptotic. C times log x plus little o of log x. I'm just changing it into an asymptotic statement. So this constant, of course, is going to depend on e, but let's not put too many subscripts. Just messes up the notation. Okay, so you get that, and so this suggests now that if I were to So this is as x goes to infinity. Infinity. And so this means now if I integrate, let's say, from 2 to 2x and subtract the result from 2 to x, you get the integral from x to 2x, of course. And that's c log 2x minus c log x. That's just a constant, but then you'll just get little of log x. Okay? Because the saving that you got by having a constant is not going to help you at all, because there's still this error. Okay, so you get something like this. Now this is also not bad, because this is telling us still that we haven't lost too much by going in this direction, because this is also telling us that psi e of t is around t. Because if I put t there, t squared, and I get log x. Ah, no, it's much smaller than t. It's even a little better than that. So you're getting something like, in this interval, you're getting something like this. So basically, it's not a surprise. I'm not going to give the details, but it's exercise in analytic number theory. Not a big deal. What is the theorem? The theorem is, or corollary is, there exists a small constant c, positive, such that, there exists a t such that for all intervals of the form x to 2x, for all such intervals of the form x to 2x, there exists a t inside that interval. There exists a t inside that interval such that psi e of t is bounded by a constant t. You will believe that, because you see, if this is t, you get log x. Sorry, you get what do you get? Well, you get log 2. You get a constant, right? Okay, you have to do this. All right, there's no. Okay, so that's anyway, we don't need such a sharp result. This is good enough. Yeah, sorry, I should have put a square root log t, because when you square it, you'll get a log x. You still want to beat that guy. So there's a t root log t. Yes, that's correct. T root log t. Is that okay? I mean, so if I think you can see the proof. The proof is if not, then this will always be bigger than this quantity. And then when I square it, I'm going to get a constant log x, and that violates the epsilon log x here. That's the idea. So you get that. And now, as you can imagine, we already, let's watch my time, we already noted that the original Birch-Swinnerton-Dyer conjecture is equivalent to the statement that psi e of t is equal to, I forgot what it was. It was little o of, I think I used an x, little o of x log x. I think this is what we already noticed that the original Birch-Swinnerton-Dyer conjecture is equivalent to this statement. And so this is definitely, if we had it for all t, we would certainly have gotten the original Birch-Swinnerton-Dyer conjecture. But keep in mind, by the way, this corollary is from theorem 1, and theorem 1 is Jung-Riemann hypothesis. So Riemann hypothesis for LES implies this result. So what does it tell us? It tells us that there is a sequence, a subsequence, on which you have a limit. See, so that's the neat thing. So therefore, we can now go back. Go back and say something. Let's see, what do we say? Okay, so theorem. So this is the main. Assume RH for LES. Then there exists a sequence, there exists xn inside 2 to the n plus 1, such that limit n goes to infinity, 1 over log xn, p less than xn, ap log p over p is minus the rank plus a half. Now this is basically what the original Birch and Swinnerton-Dyer conjecture was predict, is that this is for all x. Okay, but what we're able to show now is with the Riemann hypothesis, you can actually get a sequence of elements tending to infinity, so that this is actually the case, and therefore the corollary then would be if the limit x goes to infinity, 1 over log x, p less than x, ap log p over p exists, if this exists, if that exists, then RH is true for LES, and the limit equals minus r plus a half. So that's basically what we managed to show with all this calculation. Okay, so that's basically the content of the first part, and I think I'm okay for time right now. So this is now moving into the final stages of connecting this discussion with Nagao's conjecture. Are there any questions so far on this from anybody? Can't see.
At this moment.
Is it okay?
At this moment, yeah.
Okay. All right, so that's what we have. Now let's make some final remarks. Is my audio coming out? I mean, it's a dumb time to be asking at the end of the talk, but is my audio coming through okay? Is it?
Yes.
Well, even if you couldn't hear me, you could see what I'm writing. Okay. Now, let's see. Final remarks, connection with Nagao's conjecture. Okay, Nagao's conjecture is a different genre, as it were. And so you take an elliptic surface. So here you've got y squared equals x cubed plus a of t, x plus b of t. So this is being studied over q of t, as it were. So it's an elliptic curve over the function, this field of rational functions q of t. And of course, you make the usual estimates, conditions of the discriminant is not 0, whatnot, so on and so forth. So for each t, which is a rational number, or t and z, you get an honest to goodness elliptic curve, the kind we've been studying over the rationals. You get an elliptic curve. So what Nagao studies is a sub p of script p is 1 over p, summation t going from 1 to p, a sub p of this specialization, the specialized curve. So for each specialization, e sub t, you have a classical elliptic curve. and you have an AP associated to that. That's what we've been discussing so far. And so you've got something like this. And then Nagao conjecture, Nagao's conjecture. Oops, spell Nagao correctly. Hopefully Nagao is not watching this. Nagao's conjecture. So what is the conjecture? The conjecture is that limit x goes to infinity, 1 over x, summation p less than x, a sub p of script e, log p. There's a minus sign somewhere, but I'll put it in here, is equal to minus rank of script p over q of t. So the same result is true. So the elliptic curve over the function field, or this field of functions, has a finite rank, and we expect that this limit to be minus the rank. Now there's some sort of similarity, not quite, but some sort of similarity, as you can see from this limit is minus the rank plus a half. Don't worry about the half, it's just coming from rank and Selberg effect ideas, but essentially it's the same kind of formula. So the question is there any connection between these two conjectures? I mean, they look pretty close. They look as if they ought to be related, and sure enough, I think one could expect that. So what we could do is rewrite the Nagao sum. So we'll call this the Nagao sum. So we can rewrite that. So we can write summation p less than x, a sub p of e sub t, log p. We can rewrite that. Just shove this back in here as summation p less than x, 1 over p, summation t less than p, less than equal to p if you like, a sub p of et times a log p. Just don't worry about anything at the moment. I mean, certainly write this. There's nothing stopping you from writing that. And as is customary in mathematics, when you have two sums, you interchange. And so this is the summation t less than x, and then at of t less than x. Summation inside, we have a summation over p, and p is bigger than t, less than x. So you have AP, ET, log P over P. Hey, this is looking like the kind of sum we just finished analyzing. So this is similar to what we've just been analyzing. And so we expect from our calculation that this should be like, well, to make a long story short, especially since I'm running out of time, the RT is the rank of E sub t plus a half times the log x of t. Am I hearing the question? Any question? No. No. Okay. So we have something like this. Now this is what we have, and ignoring error terms. So this is ignore error terms. And this kind of throw this up, on the blackboard, and I'm doing a little bit of simplification, partial summation, Stirling's formula, and whatnot. We're led to the conjecture. So this is really a big question mark. It's not based on any numerical work. But is it true? Maybe it's a question, not a conjecture. But is it true that this R sub t is asymptotic to rank E of Q of t, oops, plus a half times x? I mean, that's, if we ignore error terms, that's what it would seem to suggest. If we put Nagao's conjecture, inject Nagao's conjecture, and combine it with the analysis that we just finished doing with the original Birch and Swinnerton-Dyer conjecture, it seems to suggest this. It seems to suggest this. And the question is there any reason for expecting this? And fortunately, there's some works in the literature already that are done by Philip Michel and Joe Silverman and Fermigier and other people related to this, in which seems to suggest that there might be some reason to hope that this is not a stupid conjecture. And it's possible that it's very close to that, or we're probably off by a bounded amount. That's what it seems to be. So this looks like it's something further to explore. So with that, I think it's a good place to stop.
Thank you very much for your wonderful talk. And then let's thank to the speaker first. And I can see someone raised one's hand. Oh, no. Any questions to the speaker?
I have a question. Grzegorz Banaszak speaking. Could you remind me this? You had this Kramer conjecture, this Kramer result. I mean, there was this on the right side. There was n row of a row. What was this n row? A square version.
Yeah. N row is the multiplicity of the zero.
Oh, this is what I thought. Okay, great.
N row is a multiplicity of the zero. Usually it's 1. In the case of the Riemann zeta function, it's conjectured to be 1. In the case of the L function of the elliptic curve, of course, it could be as big as the rank, but the ranks are probably not that big.
Thank you. Thank you.
And there's another question.
Yeah, can I ask something?
Mm-hmm.
Can you hear me?
Yeah, I can hear you, yeah.
Okay. So the original OBSD can be formulated as a estimation of value of Euler product, right?
Yeah, partial Euler product. Yeah, that's right.
Partial, yeah, partial. The value of partial Euler product at the critical point.
Right.
This is an estimate of this is a OBSD.
Exactly.
And can you do the similar thing for your equivalent to the Riemann hypothesis in the terms of L function?
Yes, you can. Yeah.
Can you do that?
I mean, yes, I believe that's contained in Keith Conrad's paper. Yeah. So I said when Tankuo and I had worked on this for the elliptic curve thing, and I think Keith Conrad wrote a paper that followed that, which dealt with the general situation of automorphic L functions, and so this would fit.
So it's also L function Euler product at value at one or somewhere else?
No. Oh yeah. So in those cases, it's always the Euler product at the central line of symmetry.
Yeah.
So in the case of the Riemann zeta function, it would be half.
Yes, but I'm talking about the elliptic functions, of course.
Oh, the elliptic curve, yeah. The elliptic curve.
So this equivalent. So your modified equivalent condition, OBSD, is also valued at 1.
Yeah.
Okay. So in this case, the estimate would be modified.
Yeah.
Okay.
Yeah.
Okay, thank you. By the way, okay, still, if I can, do you believe the original OBSD is true? OBSD is true?
Yeah, I believe that. I believe that.
Okay. It's not too strong to be true. It's not to be true.
No, that's the whole point.
Okay. Yeah, okay. Thank you very much, Professor. Thank you very much, Professor.
And there's another question by Larry Washington. I unmuted him.
Ron,
Yeah.
Can you hear me?
Yeah, I can hear you. Yeah.
Yeah, I was wondering, well, first of all, your conjecture at the end, it sort of goes along the line of half zero, half root one ranked elliptic curves over what you know, exactly matching that. But what I was wondering is, you had these upper bounds for psi e. Do you have lower bounds for psi e, an omega type result, Littlewood oscillation type theorems?
Right. Yeah, you do. You do.
And how close are they to your conjectures?
The Littlewood thing is that triple log x, log x, and the upper bound is log x squared.
Ah, so they're close.
They're very close in that sense. Yeah, yeah, yeah. Does that answer? Okay.
Yes, that answers. Thanks.
I think
Sorry, Mark had a question.
Yes.
Yes, if I may.
Yeah, Mark. Yeah.
Can you hear me?
Yeah, I can hear you. Yeah.
Yeah. Well, it was at the same time a remark and a question. I think it's close to what Larry said. I mean, when you look at all the specialization, so you have Joe Silverman's theorem, who tells you that the specialized rank is always at least the generic rank.
Right.
And then you have the parity question. So if you expect half of the curve to have sign -1, half of them to have sign 0, then that would explain the 1/2.
Mm-hmm.
Of course, it doesn't tell you that the rank is never is, well, that the part on which the rank would be larger is negligible.
Mm.
But what I wanted to point out is that if you sum over the integer on families, it's not always 1/2, 1/2. If you, well, there's generic condition where you sum over the rationals, where you have 1/2, 1/2 for the sign, but over integers you have non-trivial families for which the rank actually, the parity, sorry, is constant. So it seems that there must be something more subtle than the 1/2, or perhaps you should sum over the rationals. Well, there's something that doesn't match.
Mm-hmm. Yeah, yeah, I understand what you're saying. Yeah, well, I wouldn't say I had thought this, you know, extensively to give you an intelligent answer, but it seems that there's one result where I think it's Silverman and Fermichier, they seem to suggest that the error term, if you sum these error terms, it should be bounded according to their numerical work.
Mm-hmm.
So I don't know the full story on that.
There's another question by Kumar Murty.
Hi, thank you for a very excellent talk. I wanted to ask you, in the probabilistic scenario that Kramer was doing and which you are adapting, can you say anything about the higher moments of psi e?
I believe the method can be used to do it, yes. I mean, right off the top of my head right now, I can't say anything, but I know the method that he's using. And so that method seems to suggest that it's possible to analyze it, yes. And there's, I mean, I can't give you, here's the answer type of thing, but I can say that that's certainly worth looking at higher moments.
So you might be able to get the distribution.
Yeah, yeah. So maybe along the lines that has been predicted by Montgomery and Gallagher. Toward that, at least, to try to say something. Yeah, there's something about, you know, I think probability theory, probabilistic ideas, there seems to be something really at the core of all this stuff. Especially if you look at Selberg's old and new, the Selberg class, the paper where, I mean, it's clear that he's paying attention to the central limit theorem in the context of the Riemann zeta function. So there's something there, yeah.
Thank you.
So for time being, I believe it's probably better to thank the speakers of the today. First, thank you, Ram, for giving a wonderful talk. And let's thank to the speakers of the day again.